morning. As we continue talking about inverse functions today, we are going to look at the inverses of one linear one and then some simple quadratics and cubics, and look at what we need to do to make sure that the inverse is a function and how we verify that, and then how the graphs connect to each other. How does the graph of the original connect to the graph of the inverse? So that's what we're looking at today. I'm kind of hoping that you noticed something when you were doing the inverse puzzles yesterday, that puzzle piece that had the inverses and the originals both graphed together, and then they also had the line y equals x graphed on it. Did you notice anything about how they related? We're going to use that today, okay? So let's see. To begin with, let's find the inverse. No, actually, to begin with, let's review some definitions. So when I say the word function, what does that mean to you? If I say something is a function, call function. Okay, that means that it is a relation where each input has how many outputs? Exactly one. Good. Okay, so it's a relationship between two sets of values where each, you probably can't see that part. Two sets, you probably can see that far. Two sets of values. So that's like x's and y's is what I'm talking about, the domain and the range. Where each input has exactly one output. With that, when we checked graphs to see if they were functions or not back in Algebra 1, there was a nice way to check them called the vertical line test. So I'll say we check with the vertical line test. And just as a little refresher of that, that looks like this. If you have, let me just draw a little graph here. Let's say your graph does this. Let's see, how am I going to do this on screen? Okay, so take a straight edge of something and run it across the screen and check and see if my pen in this case ever hits that green curve more than one spot at a time. And it doesn't. Oh, I know a better way I can do this. Let me put it on here. Okay, so if I have this curve and I'm wondering if it's a function or not, I'll take a pen and check and see if I ever hit more than one point with my pen on that red squiggle at a time. And I don't, okay? So this is a function, okay? It passes what we call the vertical line test. Let me give you an example of one that doesn't pass it, so just so you remember the difference in the two. So, I should have said this. If you have these transparencies in your packet, I hope to put them in there. I haven't actually made them yet, an entire set of them, but hopefully I will before you actually need to watch this video. So you need those today. So let's see. Okay, let's look at this one. Okay, so I'm going to use the vertical line test. Vertical is up and down. So I'm going to lay my pen. Okay, so I have a problem right here, because you see how my pen is currently hitting 3 points on that red squiggle? This is not passing the vertical line test. So this is not a function. Each input does not have one output. I have like 3 at that point. Okay, so that's what I mean by function. You can check it with the vertical line test. Now, I don't know for sure if you would have used this term in Algebra 1 or not, but we can talk about a function being one-to-one. A 1-to-1 function. So what that means is 1-to-1, it's like an additional restriction on functions. So not only does each input have exactly one output, but if it's one-to-one, each output also has exactly one input. So there's just like one pair that goes together, and that's it. That's what one-to-one means. And you can check it. You'll know if it's a function or not by the vertical line test. If you check it horizontally as well, then you'll know if it's one-to-one or not. Okay, so like the first squiggle that I had, let me put this one back on here. We already talked about this one being a function. This is not a one-to-one function because if I lay my pen across here, that y value, let's see, my pen's probably at like -2 on this graph. There are 1, 2, 3 points where that is the y value of my pen where it hits the red line there, the red curve. So this is not a one-to-one function because there are 3 points on that red graph that have the same y value. Okay, so it's a function, it's not a one-to-one function. Okay, so there's some terminology for you. Let me get that written on here. Each x has its own y, and each y has its own x. So you can check with the horizontal and vertical line test. So it's got to pass both of those in order to be a one-to-one function. Okay, so that's background information. So let's look at finding the inverse of a simple one first. We're going to do 3 examples today of this. So for our first example, let's take y equals 3x minus 6. So I want to find the inverse of this. So I'm going to take my x's and y's and flip-flop them. Okay, so x is going to go over here. Y is going to go over here. So technically that's the inverse, but we like to have the y by itself. So we're going to solve this for y. So I'm going to add 6 on both sides. So x plus 6 equals 3y. To get the y the rest of the way by itself, that y is still multiplied by 3. So I'm going to divide by 3. And I'm going to do this in 2 separate parts on the left. I think it'll make it easier to see slope-intercept form. So I have y by itself now. So I'm going to take that y and move it to the front of the equation because I don't like having it on the back. So y equals, now in front of this x, I'm going to put a 1 right here so that it's easier for you to identify that slope. Do you see the 1/3? That's your slope. So y equals 1/3 x plus, and then if I simplify this fraction, 6 divided by 3, that simplifies to 2. Okay, so my inverse function here, so remember if you're going to write the inverse, then you want to replace the y with the inverse f of x, and the symbol for that is with the little -1 up here. We talked about that before. So it's 1/3 x plus 2. Ooh, I don't know how close that is to my picture. Let me put it over here. The inverse f of x equals 1/3 x plus 2. Okay, so I'm going to go ahead and graph those. I'm going to graph. So do this on your transparency. So you could just use regular like Crayola markers with this is fine. If you want to use dry erase, you can. But if you use just a regular marker, then you can just use a little wet washcloth, and it erases actually better than dry erase. So also, I would like to have these back when you are done with them because it's going to take me a really long time to make them, like 100 of them. So you won't want them after this year. If you really want to keep it, I'll let you. But if you don't care about it, then I would like them back. So anyway, let's graph this. I'm just going to graph the original first. The y equals 3x minus 6. So that's y equals mx plus b. 1, 2, 3 over 1. 1, 2, 3 over 1. Okay, so I have this graphed here. I'm going to hold up a white paper behind it. Hopefully you'll be able to see it a little bit better if I do that. Okay, so now here is the awesome part of having this on a transparency. It's going to help you understand the process of finding the inverse, the graph of it. So what happens when you find the inverse is your inputs become your outputs and your outputs become your inputs. In other words, your x becomes your y and your y becomes your x, right? We saw that algebraically. That's why we did the switch there. So here's how that's going to work graphically. So do you see this green dot over here where the x is? That's going to become my y-axis. And furthermore, this is the positive side of the x-axis, so it's going to become my positive y-axis. See this pink circle up here where the y is? That is currently my y-axis. That's going to become my x-axis. It's the positive part of the y-axis, so it's going to become the positive part of the x-axis. So what I'm going to do is I'm going to take this and I'm going to flip it over like so. So now what had been my x is now my y. What had been my y is now my x. Okay, so you should have it now so it says inverse function at the top. Oh, I should have told you that before. When I graphed it, I made sure I graphed it so the original was up. Sorry, I forgot to mention that. So this is what the inverse function is going to look like. I can check it very easily with this one because it's in y equals mx plus b form. So if I'm looking at the purple, I can tell that my y-intercept is 2. Yep, 1, 2. That's where that is. And then it's going up 1 and over 3. Up 1 and over 3. Okay, so that works. Furthermore, in this graph, you can tell what had been my y-intercept here is now becoming my x-intercept, and what had been my x-intercept is becoming my y-intercept. So that's the idea of the flip-flop. Okay, so I have them graphed on Desmos so that you can see them there. Oh no, did I close it? Okay, so here I have the original graphed on Desmos, so that's what we saw when we graphed it by hand, and here is what the inverse looks like on Desmos, which also matches. The thing that I want to add in here is the line y equals x. So this orange dotted line here is the line where y equals x, and can you tell that it looks like the blue line gets flipped over that orange dotted line to become the green line, that they're mirror images of each other across that line? The reason for that is that's how you found the inverse, is you took the y's and you switched them and made them the x's. So what used to tell you, the x value used to tell you how far left or right to go. Now it's telling you how far up and down to go. The y value used to tell you how far up and down to go. Now it's telling you how far left and right to go. So you've reversed those, so you've flipped it over, just like what we were doing with our transparency here for our inverse. So there is that. Another thing you're going to do today is the directions are going to say to verify the inverse by composition. So composition of functions, we talked about that. That's where you put one function inside of the other. It's where we had the chain of events, like a factory. Okay, like one factory produces something, feeds it over to the next factory, and that produces another result after that. Okay, so what we're going to do is we're going to take one of these functions and put it into the other function here. So here's how you're going to check that. So I'm going to take the original that I have in green, and I'm going to put it inside of the inverse here. So let me put some space in here. So I'm going to replace the input in the inverse, okay? And what I'm going to replace it with is the output of the original. So f of -1 of, I'm going to give myself some space first. Okay, I'm going to put these red boxes in here. Oh, and let me do one more thing. I should have probably called this original one f of x. So let me change that real quick. Okay, so what we're going to do is we're going to put the function inside of the inverse. That's composition. So I'm going to put f of x equals, now what is f of x? Well, if you look in green, it's 3x minus 6. So that's going to go right here, 3x minus 6. So if you just focus on the red boxes, can you see that I've taken the green equation, f of x equals 3x minus 6, and inserted it into those red boxes? So that's composition. I'm putting the one function inside of the other. So if I do this, I'm hoping that this right side will simplify down just to x. Because if I put the input in the first one and get an output, and then put that output in the next one, I should get the input that I started with, like the sneeches. So let's see if this works. So let's do some simplifying here. I see parentheses, so I have to distribute that. So a third of 3 is just 1. So that would be 1x. Do a little bit better erasing down here. It's probably bothering some of you. So that's 1x. A third of the negative 6 is negative 2. And then I'll bring down the plus 2. Okay. So if I simplify this, oh, look at that. The plus 2 and the minus 2 cancel each other out. 1x is the same thing as just x. So if that happens, if you simplify it down, when you put the one function inside of the other, and you get the input that you started with, which our original input is always x, then we're good. Okay, so I can say, check mark, yep, I just proved by composition that that is definitely the inverse of my original function. So let's try another one, a little bit more interesting because we're in Algebra 2 now, so we should be doing like quadratics, cubics, things like that. So for example 2, let's try, how about f of x equals x cubed minus 1. So f of x equals x cubed minus 1. Okay, so let's see, let's find the inverse first, I think. So the inverse of this is going to be, I'm going to take them and flip-flop. So where the y was, I'm going to put x. So let me do this first. Y equals x cubed minus 1. Okay, now we're going to flip-flop for the inverse. Sorry, that's sloppy. So that means I'm going to have x equals y cubed minus 1. Okay, so now I want to solve it for y. So to get that y by itself, I'm going to need to add 1 on both sides. So x plus 1 equals y cubed. And then to uncube, you have to cube root. Just like to unsquare, you square root. Well, to uncube, you cube root. So I'm going to cube root both sides. So the symbol for cube root is, it looks like square root, but you got to put a little 3 out front. If we don't put anything out front, we assume that you're just square rooting. That's the most common one by far. If you're going to put something else, some other kind of root, you have to say what kind of root you're taking. So we're taking the cube root here. On the the right hand side, the cube rooting makes the cubing go away, so that's going to be just equal to y now. And on the left hand, I have the cube root of x plus 1. Okay, so let's get this graphed. We're going to graph the original and its inverse. And to begin with, I'm going to graph it on my transparency here. So some of you might remember what the parent function of these looks like. In case you don't, I'm going to go over graphing it just by making a table. Okay, so this is my original. It's going to be important that you keep track of what's what with these. This is my original function. So x's and y's, let's put a 0 in for x. And so I'm talking about the original function here. So the y equals x cubed minus 1. Put a 0 in for x. 0 cubed is still 0. Subtract 1, we're at negative 1. Okay, I'll put a 1 in. What's 1 cubed? 1 times 1 times 1 is still 1. It's not 3, it's 1. 1 minus 1 is 0. So put a 1 in, I got a 0 out. Let's put a 2 in. 2 cubed is 8, minus 1 is 7. I'm going to put a -1 in, see what happens? -1 times -1 would turn positive, but then it's going to get multiplied by another -1, so that's -1. And then there's a -1 behind that, so that would be -2. And do I have room for one more? Oh, maybe. Let's put a -2 in. That says -2. So -2 times -2 would be -4, times another -2 would make me have... I said that wrong, didn't I? -2 times -2 is +4, but then when I multiply by another negative, it's going to turn back negative, so that's -8. -1 would make that -9. Okay, so I'm going to graph these. You go ahead and graph them too. 0, -. Okay, so here's what my original function, my y equals x cubed minus 1, looks like. So that's that S-shaped curve we saw with cubics, so that makes sense. For those of you that think about transformations, we'll be exploring that idea more tomorrow and the next day. But the -1 in this problem would be the k value, and so it's shifted the parent function, where the s is typically hinged at the origin, it's shifted that down one. So if you can see that. So here we go. Now let me get rid of this white paper here. So I want to know what this inverse is going to look like. So that means my y's are going to become my x's, and my x's are going to become my y's. So I'm going to flip it over like this. So it says inverse at the top. Here's what my inverse function is going to look like. So the s is sideways now. Okay, it's longer than it is tall. The other one was taller. Okay, so couple ways we can do this. So let's first of all, let me show you the easiest way to graph this without having to have a transparency. See this table that we have here in green, the 0, -1, 1, 0, all of that? If you have that table, oh my goodness, making a table for the inverse is so easy. So the inverse would be a flip-flop of that. So we're just going to take the x's and the y's and flip-flop them. So instead of 0, -1, it's going to be -1, 0. Instead of 1, 0, it's going to be 0, 1. Instead of 2, 7, it's going to be 7, 2. Instead of -1, -2, it's going to be -2, -1. Instead of -9, it's going to be -9, -2. So, ta-da! That is probably the easiest way for many of you to find what the inverse is going to be. You did all the work for the regular function, just flip-flop them for the inverse, okay? That will be probably for most of you your favorite. Now some of you are visual learners, so let me give you another way to think about this. So let me graph the original on here. Y equals, what was it? X cubed minus 1. So there's the original there. Here I can turn the y equals x off for a little bit, but we'll need that again in a minute. Y equals... Okay, so this, we had the cube root of x plus 1. So on Desmos, to get cube root, you're going to go down to the keypad here. Square root shows up right away, but cube root isn't used as common. So they have it tucked over in the functions. So you're going to have to go to the miscellaneous functions. Okay, and then look in this middle column here. Do you see the one with the n? That's going to let you put different numbers in for the cube root. Or, well, because you could do 4th root, 5th root, whatever. We want a cube root, so I'm going to put a 3 there. And then we want an x plus 1. Okay, so this is kind of cool looking, I think. Let me put the y equals x line back on there. Here, do you see the symmetry? Do you see how the purple one has gotten flipped over the orange dotted line to become the black one, they're inverses of each other. They like mirror each other over that diagonal line. So some of you might prefer, instead of taking the table of numbers and flip-flopping those columns, some of you might prefer to do this visually, to sketch the original, draw your diagonal dotted line on there, and then sketch what the mirror of it would be. So if you are a picture type person, you might like that approach better to graphing the inverse of it. And it's fine if you do. Let's see. Oh yeah, we should prove that one by composition. So to do this, I get a new page here. So my original, I'm going to put my original in green. It was x cubed minus 1. And I'll put the inverse in purple. It was the cube root of x plus 1. And so let me give myself some room here to think. So I'm going to put the original function, the green, into those red boxes. Now what am I trying to prove here? What am I hoping that this is going to simplify to? I'm hoping I'm going to end up back with x, because if I run something through the original and the inverse, I should be back to where I started. So that's what I'm hoping to see happen. Okay, so there's the same thing written. Oh, I forgot my red box over here. There, with some space to work. So into those red boxes, I'm going to insert my original function. So on the function notation side, I'm going to put the f of x. And on the equation side of it, I'm going to put the x cubed minus 1. Okay, so now I need to simplify the right side. So I don't need that red box anymore. Let's see if I can erase it. Oh, no. I don't think I'm a good enough eraser to erase it. So we're just going to leave it kind of there. So do you see the minus 1 plus 1? Okay, they're going to cancel each other out. So that goes away. Then you have to cube root the x cubed. Well, the cube rooting and the cubing undo each other, so that gets you back to just x. So check, we did it! Woohoo! That proves by composition that we have the correct inverse, that is the inverse function, because I got back to just x. Let's do one more. Oh wait, yeah, I showed you those on Desmos already. Okay, so our third and final example, we are going to look at y equals x squared plus 3. Okay, so that's my f of x. I should have put f of x there. It's my original. So let's graph this one first. I want you to see something about this first. So I think you'd be okay doing this, thinking about our transformations. So I see an x squared, so we're talking quadratic. So quadratics look like what? Yeah, those are parabolas, so you're going to see a smile or a frown here. We talking smile or we talking frown? Yes, this will be a smile because the x squared is positive, so that's going to make you smile. That plus 3 is going to shift it up 3 spots. So the vertex is going to be right here. And then, do you remember our patterning of the parent function parabola where it went up 1 and over, up 3, up 5, up 7, like that? I'm just going to use that to make my pattern here. Up 1, up 3, and then, of course, they're symmetric, so you can mirror things. Okay, so here's my original function, my parabola. It's the graph of it. So, is this a function? Does this pass the vertical line test? This is a function, it's fine. Is it a one-to-one function though? Let me check. Nope, see how my pen's hit in two places? This is not a one-to-one function. That's going to come up in a minute, okay? So I wanted to point that out. So the inverse, let's see what the inverse of this is going to look like. My y's are going to become my x's, and my x's are going to become my y's. So I'm going to flip it over like this. So here, so you can see it better. This is what my inverse would look like. Now, is this a function? Is this, can I call this the inverse function? Well, let's check and see. No. Okay, so this is a bit of a problem because sometimes mathematicians need to work with functions because like computers, for example, like to have one output for an input. Okay, they like functions. They like to be able to know what will happen as an output. They don't want two different outcomes. Okay, so this poses a problem because the inverse, that's the inverse, but I can't call it the inverse function. Okay, why not? So let me look back at the original. What is it about this that makes it not going to be a function when I flip it over? You see it? Well, it's the mirror image idea, isn't it? If I could get rid of this side of it, I just looked at half of it and didn't have the mirror image over there, and then I flipped it over. Let's see if I can do this. And then I took it and I flipped it over. Then, if that's what I saw, would that be a function? Yeah, then it would be okay. All right, so this, in order to make the inverse a function, we're going to have an extra step here, and it's going to be called restricting the domain. Okay, so this, I'm going to write this down here. So let's restrict the domain. The domain is that the x's or the y's? That's the x's. Oh, I don't know what those extra dots are down there. So we're going to restrict the domain. It's so we don't see the mirror image. Of the parabola. Okay, so what I mean is we could actually technically we could look at that part or we could look at this part. Either way, when I do the flip, I wouldn't get something that was not a function. I would get a function. However, we're going to choose which side of these we're going to use, okay? Now, answer me this. Would you rather work with positives or negatives? Okay, I know that you were thinking positives. If you said negatives, then you're just like trying to be stubborn. Because I know everybody likes positives better. So, if we have to choose between the positive half, because this is where the x's go positive, and over here is where the x's go negative, we're going to choose the positive half, okay? So we're going to restrict it from the vertex over, where the x value of the vertex is. So that would be from 0 over to the right. So we will limit from the vertex and go right. So in this case, we want to go, we want to go from x, where x is greater than 0. That means I'll keep the part that's on the right of the vertex. X is greater than 0. Okay, so I'm going to erase this other part of my parabola. So I'm going to limit the domain on the original so that I can do the flip and get a function, okay? It's now a function because now when I run my pen across it, each input only has one output. So that's good news there. So there's that. Let me think what else I need to say about that. Oh, we didn't find the inverse yet, did we? Okay, so it was f of x equals, what was it? X squared plus 3. And so we're just keeping the part where x is greater than 0. Just putting that domain back there. Oh, I should have put it in the fancy brackets. Anyway, so now I'm going to write this as a y. Oops. Now I'm going to do the flip-flop, so x equals y squared plus 3. So technically that red line is the inverse, but I would like to have the y by itself, so I'm going to subtract 3 on both sides, so x minus 3 equals y squared. Now to unsquare, we'll have to square root, so y equals the square root of x plus 3. So there's my inverse. I think you're getting the idea. I hope you're getting the idea of plugging the one into the other to check, to verify by composition that the inverse is correct, is how you will be asked to do that. Now let me go over to Desmos for a second, because I'm going to show you this. Is x squared plus 3. And the okay, so let me show you this. If I just do the flip-flop, if I just say x equals y squared plus 3, no, x, what am I doing? Yeah, plus 3. So that you can see the mirror image of that parabola getting flipped over the orange dotted line to become the sideways parabola. Can you tell that the red one is not a function right now? When we solve this the way that we just did, and we have y equals the square root, let me go down here and get the square root symbol, of x minus 3. Okay, let me show you this. So let me turn off the original, turn off the red line, just so you can see these two. So the red was when all I did was I flip-flopped the letters, but I hadn't solved it for y yet. If I turn the blue on, do you see how it's just the upper half of that parabola? That's what happens when we've limited the domain to just the positives on the original one, so that I just get the part that's a function. So that's how those two ideas connect. So, okay, I think that is everything. I know that was a lot today to take notes on, but I hope that you know that Jesus loves you, and so do I, so do your math.